We will now leave infrared spectroscopy for a while and turn to another variant of vibrational spectroscopy, which is Raman spectroscopy. Raman spectroscopy is based on Raman scattering, also named Raman effect, that was discovered 1928 by the Indian physicist Raman with help of the bright sunlight in India. Very soon afterwards he received the Nobel Prize in Physics for his discovery. He was also knighted in 1929 by the Queen of England and became Sir Raman. In Raman spectroscopy, light that is inelastically scattered is detected. Inelastic scattering means that the scattered photons have a different energy than the incident photons. This scattering is called Raman scattering. The figure shows a hypothetical spectrum of Rayleigh and Raman scattering from a simple compound. Most of the light that is scattered is elastically scattered, which means that the scattered photons have the same energy as the incident photons. This is Rayleigh scattering. However, some of the photons have less energy and some have more energy than the incident photons. This is Raman scattering, which gives rise to additional lines in the spectrum of scattered radiation. If lines are found at smaller energy than the Rayleigh line, they are called Stokes lines. If they have more energy, they are called anti-Stokes lines. It turns out that the energy difference between the Rayleigh photons and the Raman photons, shown here, corresponds to the energy needed for vibrational transitions of the scattered molecule. Scattering is a rather unlikely process. The probability for Rayleigh scattering is 10 to the power of -4, meaning that only 1 out of 10 to the power of 4 photons is Rayleigh scattered. Raman scattering is even less likely. The probability is about 10 to the power of -9. This is a disadvantage of Raman spectroscopy, because only a very small fraction of the incident photons generate a Raman signal, which limits the signal-to-noise ratio. What is the origin of the Raman bands in the spectrum of the scattered photons? This is easy to understand in the quantum mechanical view, which is illustrated in this figure. The figure shows the vibronic states of a molecule for the electronic ground state, here, and for the first electronically excited state, as well as the three processes Rayleigh scattering, Stokes-Raman scattering, and anti-Stokes-Raman scattering. It is assumed in the figure, and common in Raman spectroscopy, that the photon energy is less than required to excite the molecule to a higher electronic level. In all of these processes, an incident photon interacts with the molecule and excites it to a virtual state. The photon becomes annihilated in this process. The virtual state is a non-stationary state of the system. It has therefore a very short lifetime, and its energy is not well defined. When it decays, the scattered photon is created. The three processes differ in the energy of the scattered photon. In Rayleigh scattering, indicated by the green arrows, the photon energy of the scattered photon is the same as that of the incident photon. Therefore, there is no net energy transfer between radiation and molecule, and the final state of the molecule is the same as the initial state. In Stokes-Raman scattering, the energy of the scattered photon is less than that of the incident photon. The energy difference is used to excite the molecule to a higher vibrational state. Only transitions to the next vibrational level are allowed in Raman spectroscopy. This is the same selection rule that applies for the absorption of infrared radiation. Therefore, the difference in energy between the incident photon and the scattered photon matches that of a vibrational transition h nu Vib. As most of the oscillators are in the vibrational ground state at room temperature, the most relevant process for Stokes-Raman scattering is from the vibrational ground state to the first excited vibrational state. In anti-Stokes-Raman scattering, the molecule is initially in the first excited vibrational state, and after the scattering process in the vibrational ground state. Therefore, the energy of the scattered photon is higher than that of the incident photon. Anti-Stokes scattering is unlikely because only a few oscillators are in an excited vibrational state at room temperature, which makes the intensity of anti-Stokes lines small. Raman scattering is greatly enhanced by a factor of 100 to 1000 when the incident light energy is close to the energy of an electronic transition. This is called resonance Raman effect. In resonance Raman spectroscopy, a photon is first absorbed and then emitted. This is slower than normal Raman scattering, but still quite fast. Emission is therefore from the same vibrational state that was reached upon excitation. This is different for the emission of fluorescence photons, where after excitation, there is first vibrational relaxation to the ground state, vibrational ground state of the first excited electronic state, as we will discuss later in the fluorescence lecture. As said, in contrast, in resonance Raman spectroscopy, the emission of the photon is faster than the relaxation of the vibrational levels back to the ground state of the vibrational levels of the electronically excited state.